Yeah. Prakash. So I'm an alumni of your college. So I completed my BTech in computer science in 2013. Sandil Kumar sir was my mentor, class advisor, etc. And yeah, right now I'm working in a bank called Synchrony Financial. So I started my career in Mu Sigma as a decision scientist, and from there I switched to banks. I worked in a couple of banks like HSBC and Wells Fargo, and right now I'm with a bank called Synchrony Financial, where I'm into credit risk analytics. So yesterday we had a session on the preliminary concepts like types of data, different kind of tests and hypothesis testing, etc. In this session today, we would look into various steps involved in uh, while developing a model and how to choose a different variables for a model and how to assess if a model is good or not, etc. Um, we'll probably get started with it. Let me share my screen. I hope my screen is visible.
Yes, sir. Yes.
Sure. Yeah. Let's get started. So, as I said, we'll look into a brief introduction to what is modeling, etc., and different kinds of modeling. And the prime focus today would be on the steps involved in modeling and how to assess if a model is good to use. So, in case of modeling, as you know, um, it's a step or it is a model is nothing but a framework which accepts some inputs and gives some output. In this in machine learning or data analytics parlance, what we mean here as a model is that it's a set of equations or a set of rules or something like that, which takes the input that we have, learns from it, or does some operations on this data and gives us um, whatever is the expected output. Let's look into different types of models in case of machine learning. The two broad classifications of models are supervised and unsupervised learning. In case of supervised learning, we already have the model with some labels or with some definitions, and we train the model with that labeled data, and which is in modeling term which is called a dependent variable, and we try to um, uh, train this model with this labeled data, and try to apply this model on a different set of new data which does not have this label, and the objective of the model is to predict this label for those which does not have this data. So so going by the definition, the goal of a supervised learning, it is a mapping function which predicts the output for new or unseen inputs based on the training data set. So classification and regression are examples of this. So a few real life examples being trying to create a model to predict who are all the likely customers to buy a new product based on the historic customer base data set, or trying to find who all are likely to um, default payments based on their historic payment behavior in a bank, etc. Now, it could also we could also see try to predict things like sales, etc., based on the historic sales data. So, in which case it would be a regression problem. Now, in case of unsupervised learning, we will not have this label or definition as such. We'll just have an input data set. The model is supposed to understand the, analyze the data, identify patterns, structures, etc., and come up with the outputs by itself without any training as such. So examples being clustering, dimensionality reduction, etc. So mostly unsupervised is used in cases like segmentation, where we have um, a large data set, and we would like to segment, let's say we have a customer data set, and we would like to segment them into homogeneous groups, the smaller homogeneous groups, and then try to target um, individual groups separately if we don't have enough budget to target the entire population. uh, and if we don't have any historic information about these customers, let's say we are trying to launch a new product, and we don't have any customer base for itself, and we just have some borrowed customer information, which also does not have any information about this new product as such. In those cases, basically, if we don't have any historic information that we are looking for, then we would go for unsupervised learning. So in today's session, we will focus more on supervised learning, um, and the various steps involved in supervised learning. And during the process, we will also touch upon few concepts like sampling and correlation. Various types of sampling and two different kinds of correlation, etc. So the very first step involved in modeling is to have our objectives fixed. Like, what are we trying to model? So and define that um, objective, properly define that objective and create the dependent variable accordingly. So let's take an example of a credit card company. So if our objective is to identify or predict the customers who are going to default, then here the dependent variable is the uh, set of existing customers who have who let's take the example with the data we have current last 1 year of credit card data. For example, let's say we have last 1 year of credit card data. So we have the things like whether the person had defaulted or not, also along with other things like how many times the credit card was used, how much balance was used, how much was the credit limit, and out of the total credit limit, how much was used, which is the utilization, and the customer's CIBIL score, the customer's relationship balance, etc., etc. So these are all the independent variables based on which we are going to predict if the customer, if a new customer is going to default or not. So in this case, although we are saying that we would like to predict the likelihood of a person defaulting, we need to quantify it further. Like, um, what does default mean? So in some cases, a person missing 1 month due might be considered as default. In some cases, probably a person defaulting 3 months of credit card dues might be considered as default. So we need to fix what is the target, or what we are trying to model, and create create a flag which is the dependent variable based on the objective that we are trying to model. Let us take a person defaulting 3 months due in a credit card as dependent variable. So in the last 1 year of performance data that we have, I mean customer data that we have, wherever a customer had defaulted more than 3 times, I mean 3 dues, we would mark all of them as ones, and the remaining would be zero. So this is going to be the dependent variable or target variable, and which is what is going to be, I mean, likelihood of this variable being one is what the model is going to predict. And another example being, if let us say we are going to predict sales, even in that case, we need to define the define it I mean come up with a proper target variable, where if for example we have last 5 years of sales data, and we are trying to predict the sales in the next 1 month. So we cannot use the sales data directly as the dependent variable. We need to define the units of sales, whether it's going to be annual sales or whether it is going to be monthly sales, or so on, and create one variable which is going to be the variable that we are going to predict. Let us say we are trying to predict the sales, or let's say we are trying to predict the sale of onions in kilograms in a particular department store in next 1 month. Our data set has data in let us say it is in pounds, or let us say it is in tons of data. So we need to first convert it um, into kilograms, and also suppose our data is at day level data, daily sales in a departmental store. We need to first convert that into monthly sales. uh, Basically the point is we need to make sure that the level of data is correct and the unit of data is correct, and the target variable is to be defined properly in such a way that it meets our business objective. So defining the target variable is the first and most important thing in the model, because based on this the model gets trained, and then in the new data the predictions happen. So if we um, do I mean if we do not define the target variable properly, then the whole modeling exercise is going to fail. Now, once the dependent variable is set, now coming to independent variables. So we need to do data cleaning. So there is a possibility that there are some values missing in some rows, or in some columns, or in several columns. So we need to fix those. When we feed the model into the, I mean, feed the variables into the model, we should not have any missing values. So let us suppose we have around 1% of data missing in few columns. So we need to understand, I mean, based on the type of data it is and based on the business context it has, we need to decide how are we going to treat these missing values, whether we are going to put 0 as the default value wherever it is missing, or whether we are going to put 1, or whether we are going to put the average of the non-missing values in the missing values, I mean wherever the value is missing, or whether some other centrality like median or mode is to be put there, needs to be defined, and this needs to be decided based on the business context and what variable it is and what type of data it is. For example, if it is a 1 0 variable, it doesn't make sense to let us say it is we have 1,000 rows, and in 20 rows values are missing, and in the remaining 980 rows we have ones and zeros. It doesn't make sense to take average of ones and zeros and put in these 10 rows. We need to put one or zero only. So the point being, we should take into consideration the data type as well when we try to do missing value treatment. Now comes the outlier treatment. So based on the data, if we find that there are some outliers, it is better to treat those outliers, because these outliers would impact the model in undesirable way. Let us say we take this credit card example itself, and let us say relationship balance is one of the dependent variables, and out of 1,000 rows we have, let us suppose one person alone has 20 crores balance, and remaining all are having around 10,000, 15,000, 20,000, etc. as the balance, but one person alone has 20 crores as the balance. Now the model would get hampered because of this one data point with the 20 crores, right? So it is better to uh, treat it, remove, one easy thing to do is just remove this row, and of course this the treatment is applicable to missing value as well. If the number of rows in which the data is missing in one or more columns is very less, then the best missing value treatment is to remove those rows completely. But only in those cases where we cannot afford to remove, we need to go for some kind of other treatments. Now, again, in outlier treatment, we need to decide whether we need to, like in this particular case, in the place of 2 crores balance, like we need to decide whether to put the average balance of the remaining 999 people into this person also, or should we take the maximum of balance among the remaining 999 and put that maximum value here, or something like that needs to be done, or the average of top 5 balances, something like that needs to be put. Putting something like that would make more sense rather than going ahead with the 2 crore balance itself. Now, how to know if there is an outlier? We can, we need to plot the data, it plot each of these dependent variables, independent variables in a box plot. In some there is something called box plot, which shows the values by percentile, what is the 50th percentile value, 60th percentile value, and so on. So by plotting the dependent variables in a box plot, we could get a pictorial representation of whether there are any outliers. We could kind of quantify it, like see what is the percentage of values with such outliers. We could also do a normal scatter plot and see, and if we see that one point alone is too far from the remaining data points, then we could consider treating it, if we could, if the business if it makes business sense to do so. Now, once we have the dependent variable and the dependent variable defined and the independent variables all cleaned, now next step is to see if we can go ahead with the entire population that we have, or should we do some kind of sampling. So now sampling is required in two scenarios. Number one, let's say we have a big amount of data, like running into several million rows of data. So for example, if we are trying to predict whether a transaction is fraudulent or not based on historic transactions data in a credit card company. So the usually these transaction data sets used to be very huge. It runs into millions of rows because there are several thousands of customers, or in fact, if the bank is big, there would be several lakhs of customers with one or even multiple credit cards, which all of which they would, I mean, even if 10% of people use the credit card 2 or 3 times a day, uh, we can imagine how many rows of data would be there in the transactions data for a period like 1 year time period or 2 years time period. So probably it's not possible for us to uh, use that entire data for modeling. So in such cases, we need to use sampling to reduce it to a reasonable number, which our tool can handle, modeling tool can handle. So this is one scenario where we need to use sampling. There could be there is another scenario where we might need to use sampling. So let us take, I mean, this scenario is applicable only in case of classification problems and not in case of regression problems where we are trying to predict integers like sales or height or weight, etc. But in case of classification problems where we are trying to predict one probability of 1 or 0, etc., like trying to predict if a customer is going to default in next 1 year or so, in such problems this second scenario of sampling requirement comes in. So the data set should have a proper balance between, I mean, the training data set should have a proper balance between the number of ones and zeros. It shouldn't be the case that we have 10,000 records, out of which 9,980 are having zeros, and only remaining 10 accounts, I mean 10 rows are having ones. So in which case the model will not be able to actually find any patterns, any differentiating patterns between the rows with ones and rows with zeros, because I mean, it's a comparison between 9990 rows and 10 rows. So in which case we need to do some kind of sampling to bring balance between ones and zeros. So usually it is advisable that we do not go ahead with a data set with more than 1 is to 10 good is to bad, or 1 is to 0. So usually in any kind of data set we used to have more of zeros and less of ones. So in case of customer in case of this customer going default in next 1 year again. So in the historic data also, if we see, we will find more of good customers than bad customers. So we will have lesser ones than zeros. That's the nature of the data set. But still, um, we should make sure that we do not have more than 10 times of zeros. So compared to one. So let's say we have only 100 ones in the data set. Although we have 10,000 records with 100 ones and 990, I mean 9,900 zeros, it is advisable that we take the entire 100 ones, and out of the remaining 9,900 zeros, we take a random sample of 1,000 alone and go ahead with the model. I mean, go ahead with modeling with this 100 ones and 1,000 zeros alone. So such a way that the ratio between ones and zeros is 1 is to 10. So otherwise, I mean, inverse scenarios probably 1 is to 15, but going ahead with a model with more than 1 is to 15 ratio between 1 and 0 uh, is generally not advisable. Now, when it comes to sampling, there are different different kinds of sampling techniques which are available, and we need to choose whatever is most appropriate for our scenario. So the 5 common sampling techniques are these randoms, systematic, and so on. So let's see each one of them quickly. So random sampling is the most common thing. We just select data points, I mean how many ever data points we want from the population randomly without any specific criteria. So in this case, each data point gets an equal chance to become a part of the sample. I mean sample set that we choose. Now, second one is systemic. Systemic is a type of sampling where we select data points at equal intervals. Like, for example, we choose a random data point, let's say first data point or second data point, and we choose every 10th data point from the first one, or every 20th data point from the first point, and so on. Only the first point or the starting point is selected randomly, and then the remaining points are selected based on the fixed intervals from the first point. I mean, first selected point. Next is stratified sampling. Here we divide the population into homogeneous or similar subgroups, and then within each subgroup we randomly select data points. We select, I mean, the number of data points selected in each group depends upon the number of, I mean, the depends upon the representation of the each subgroup in the overall population. For example, let's say we have 1,000 balls um, in the population. We have let's say we have 600 red and 400 blue color balls, and we need to select out of this 1,000. We need to select 100 balls representing the overall population. So in which case we first split the 100, I mean 1,000 balls into 600 red and 400 blue, and select 60 from the red and 40 from the blue, such a way that the ratio of red is to blue is preserved in the sample as well. Each data point has equal chance of getting selected, because we are preserving the representation, I mean we are preserving the ratio of the uh, ratio of each subgroup. The chances of being selected is again the same. Now, next comes the clustering method, where we divide the population into clusters, and instead of selecting few data points within each cluster, what we do is select few clusters on the whole. So this is the difference between stratified and clustering. So in both the cases, we divide the population into smaller chunks, but in stratified, we select a few random samples within each subgroup, whereas in clustering, we just ignore a few clusters and we just take a few clusters in entirety. So this is used when it is very difficult to collect samples from the entire population. So for example, if we are trying to get samples of I mean, collect samples from different districts across India, samples of anything for that matter. Let's say literacy or quality of education or whatever it is from each district of India. What we do is we just take from uh, few districts and consider that to be a representative of all the districts. Next comes the convenience sampling. So convenience sampling is used when there are again restrictions in collecting data. So based on the availability and accessibility, we choose the samples. So for example, let us say we are supposed to estimate the number of trees between, let's say, Coimbatore and Chennai. Between Coimbatore and Chennai, the distance is 500 kilometers. It's not possible for anyone to uh, travel the entire 500 kilometers, and I mean, it is possible to travel, but it's not possible for anyone to keep counting as we counting the number of trees as we travel. So what one can do is split this 500 into 100 chunks of 5 kilometer each, or 500 chunks of 1 kilometer each, and count the number of trees in few samples of 1 kilometers, and take that as the representative of the entire 500-kilometer stretch. Now, when it comes to convenience sampling, if we are in Coimbatore, it doesn't, I mean, we'll probably choose 1 kilometer stretches in and around Coimbatore, maybe 1 kilometer in Coimbatore, 1 kilometer somewhere near Avinashi, etc. But we probably would not travel midway, or we probably would not select this 1 kilometer stretches randomly, or try to select from every 50 kilometers, 1 kilometers, and so on and so forth. We will not do, but count near our place wherever we are. So this is convenience sampling. Now, based on the model that we are trying to build, whatever is the sampling technique which is appropriate, that needs to be applied, and come up with the final data set. Once we have the final data set, I mean, this data set is what is going to get fed into the model. Now is the time to decide what all dependent variables which are appropriate. Now, dependent variables, we would, I mean, in case of this credit card, it's an example again. So, for example, when we are trying to predict the likelihood of a customer going default in the next 1 year, that dependent variables could be, I mean, independent variables could be things like his relationship balance, CIBIL score, number of times he had defaulted in the past, etc., etc. Now, I mean, I'm just able to tell few examples, but in real life we might have thousands of independent variables, or at least hundreds of independent variables. Now we need to choose what makes sense statistically, as well as whatever makes sense as per business sense as well, and choose only those which makes both statistical and business sense, and use those alone into the final model. There are a few steps to finalize the independent variables. The first one being, I mean, the first step is to find if there is a statistical relationship between the independent variable and the dependent variable, and the metric that is used to do that is correlation. So in case of correlation, it measures the strength and the direction of the relationship between the two variables. So this correlation technique needs to be done for each of the individual, I mean, each of the independent variables with the dependent variables individually. So if there are 100 independent variables, we will get 100 correlation numbers. So for each pair of the independent variable with the dependent variable. So correlation takes a value between -1 and +1. -1 means a perfectly negative correlation, and +1 means denotes a perfect positive correlation. For example, if height and weight are the two variables, in most of the cases when the height increases, weight also increases. I mean, assuming the density is the same. So in these cases, in this case, it's going to be a positive correlation, where when the height increases, weight increases, and the opposite as well. But whereas, let us say, time and speed, time taken to reach a point, and speed of travel. So when the time, I mean, when the speed increases, time decreases, and the opposite, when the speed decreases, time increases. So this is an example of negative correlation. So there are two correlation, I mean, two ways of, I mean, two different correlation metrics. One is Pearson's correlation and the other one is Spearman's correlation. So in case of Pearson's correlation, it is the measure of getting the relationship between the two variables uh, directly. It tries to define the actual linear uh, relationship between the two. So for example, if there is an increase of 1 unit in one variable, how much is the increase or decrease going to be in the other one? So that kind of actual linear correlation is Pearson correlation. Whereas in case of Spearman correlation, it does not consider about the extent of relationship. It just um, considers the direction alone. So if one increases, whether the other one increases or not alone is considered in case of Spearman correlation. So it basically instead of trying to find the correlation directly on the raw variable, it first ranks the two variables, and the correlation between the ranks is what is the Spearman correlation. We'll quickly look into one small example for correlation alone. I mean, for the two different correlations. So, I mean, this is an Excel spreadsheet with 10 data points. We have max and science marks of 10 different students. Now, Pearson correlation is nothing but direct correlation between this column and this column. And we see that the correlation is 0.91, which is close to 1. So someone who is scoring good marks in max uh, is scoring a good mark in science as well. Now, in case of Spearman, instead of applying the correlation directly on the marks, we calculate it. We first calculate the rank. So rank in Excel, we could calculate using the rank function. So as you see, someone who has got the 100 marks has got the first rank, and someone with the lowest mark 60 has got ninth rank. So similarly, in case of science as well, science rank is based on science marks, and max rank is based on max mark. And the Spearman correlation is the correlation between max rank and science rank. So here, as I said, here the amount of difference does not matter. Here, whereas it's just uh, it's just about the direction. Someone who has got first rank in max, what rank it is he has got in science is the only measure we are trying to see here. Whereas in case of the other one, if someone has got 100, how many marks as such, like whether it is 97 or I mean whether it's going to be 90 or 60 or so on, that actual linear relation is what is measured in case of Pearson. So in case there are outliers, Pearson correlation has, outliers impact Pearson more than in case of Spearman. Let's look example. So someone who has got 100 in max, let's say he has got only 10 marks in science, the correlation immediately drops from 90% to 1.9% in case of Pearson. Whereas in Spearman, the impact is not that much. It has reduced. It will reduce, but it has not reduced as much as in case of Pearson. Now, going back to modeling uh, steps. So, first step to finalize the independent variables is to look into the correlation. So, out of the 100 variables, we need to first remove those variables which does not have any kind of correlation. I mean, whether positive or negative doesn't matter, but some kind of correlation should be there with the independent variable, sorry, with the dependent variable. So we need to remove those variables which does not have any kind of correlation. So that is the first step in choosing the uh, independent variables. So we could generally we use 0.8 or zero point 0.7 as the cutoff. But anyway, based on the values that you get, you could choose the appropriate cutoff. So anything with more than zero point 0.8 or less than minus 0.8 would be preserved, and remaining would be discarded. That's the first step. Now, after this exercise, let us say we end up with 40 variables out of 100. Now we need to further reduce it. So in which case we use multi-correlation. Multi-correlation is nothing but the correlation among the dependent variables in itself. So out of the 40 variables, we calculate the correlation between each of them. So we would get a 40 by 40 matrix, which will tell the correlation between first variable with all the remaining 39 variables, second variable with the remaining 39 variables, and so on. So we do this and remove those set of I mean, if we find multiple pairs of variables which with very high correlation with each other, we have to preserve only one of the two and remove the other one, because it doesn't make sense anyway. The one of the two is having very high correlation with the other one, so there is no reason to have both. So this way we could get rid of some more variables. And then the last one is p value. So now coming back to hypothesis testing that we saw yesterday, we start with the null hypothesis that these independent variables do not have any impact on the dependent variable. Now, if the p-value is small, then we need to reject the null hypothesis, which means the variable, which means the alternate hypothesis is true. If the null hypothesis is that the variable does not have any impact on the dependent variable, alternate hypothesis is going to be that the variable has good amount of impact on the dependent variable. So if p is so small, we would reject it and reject the null hypothesis, which means we need to accept that variable. So if there are variables with very high p value, in those cases we cannot reject the null hypothesis that the variable does not have any impact on the dependent variable. So we need to remove those variables with high p value. So these are the different types of methods, I mean different types of metrics that we need to use to uh, quantitatively or statistically remove variables. Now on top of this, we need to keep in mind the business impact or business reason between I mean, whether it makes business sense to keep these variables or not. That's the most important thing. And we need to remember that correlation does not mean causation. So whatever makes business sense, whatever you think would have a direct impact on the dependent variable in terms of business as well, only those variables need to be kept in the model. And based on the modeling objective, whether it is to predict the sales or sales or marks or something like that in terms of linear thing, or if it is going to be a classification problem, different types of algorithms are to be used, starting from linear regression, logistic regression, decision trees, and so on. Now we have different machine learning algorithms as well. So the based on the type of the dependent variable and what objective you are supposed to meet, the appropriate model is to be used. um, and finally, uh, at the end of the day, we need to assess whether a model is good or bad. And to do that, in case of a linear thing, we usually use something called a MAP as a metric to assess the goodness of a model. MAP is nothing but mean absolute percentage error. This is calculated based on the actual and predicted values. So the actual is A and the predicted is F. So difference between actual and predicted, it's absolute difference in terms of percentage. So divided by actual, and this figures average. This is a measure of how far the model has predicted compared to the actual values on an average. So this is the map should be as less as possible for a model to be good to use. So this is used when we have multiple models. The model with the lowest map is to be used. Now, in case of classification problems, as we saw yesterday, we have things like I mean there are four possibilities. If the predicted and the actual both are positive, or one is positive and the other one is negative. So based on that, we have true positive, true negative, false positive, and false negative. There are three metrics based on these true positives and these four things, out of which precision is a measure of out of total positives, how many are we able to predict in this model. So it's a true positive divided by true positive plus false positive. And I'm sorry. So precision is a measure of out of how much we predicted as positive, how many are actually positive. So that's why it is true positive plus false positive uh, in the denominator, and the true positive is the numerator. And in case of recall, out of the total positives which are present in the data, how many have we actually recalled? How many have we identified as the positives? So it is true positive divided by true positive plus false negative. And in case of accuracy, it's nothing but the sum of greens divided by total. So true positive plus false negative, true negative divided by all four. So this is accuracy. So based on the uh, business requirement, we need to use the model which has we need to choose which of the three is more accurate, and uh, whichever metric we finalize, out of that metric, whichever has the highest number, whichever model has the highest number among the available choices, we need to use that model. Now, given that there is not much of time, we could not actually see any working example as such. In case of some other opportunity in future, we will have a take a live example. We will take a proper data set from Kaggle or something, and define the independent variable, dependent variable, different independent variables, find the correlation, etc., and use some tool to actually develop a model and do the model assessments as well. So we'll do that in a different occasion. So I think we are already out over time. Unless you have any questions, we'll open it up for any kind of questions. And I'm I'm good with this. So in case there are no questions, I think we could wrap up
Yeah,
at this point.
yeah. Thank you, Om Prakash. It was nice. I think it will help people to understand how to model data and present it in real time. Thank you all. Om
Thank you,
Prakash,
sir.
thank you.
Thank you for the opportunity.
Yeah, good day.